All right, so in this video, we are going further in our effort to quantify the energetic state of a system, and we're going to talk a little bit about the dynamics of potential energy changing throughout our system here. So what did we learn last time? Last time we learned if we have conservative forces and an isolated system, that our total mechanical energy at any two given states, our mechanical energy at state 2 is going to be equal to our mechanical energy at state 1. You can think of those as final and initial states or anything in between. And so we know that we have KE2 plus U2 equals KE1 plus U1. And what do we have in terms of definitions of these U's and KE's? Well, for U's, we have a gravitational potential energy. That's U. U is the potential energy, and so that's the mass times the gravitational constant times our height. And our potential energy from a spring is 1/2 the spring constant times the compression or the expansion squared. We also have our definition for kinetic energy in general, and this is energy stored as motion or energy spent on motion, and that's 1/2 the mass times whatever the velocity that your object is going squared. And we won't want to forget our definition, our general definition of work, which is force over a certain distance. Okay, so the example that we're going to talk about to frame this video and sort of unpack these ideas is going to be the example of a spring, a mass compressing with a spring. And so just to draw that out here, we're going to talk about a couple of different scenarios with our mass and spring. So here is some surface with a wall attached to it, and here is our spring. There's our spring, and that's attached to some mass, m. And this spring has some spring constant, k. It doesn't have to be pretty, but it's still a conservative spring, and that's all we care about. And so what's going to happen as this to the potential energy and kinetic energy mix in the system as this thing starts moving? So if we, let's say, extend this system out and then let it go, we want to track what exactly is happening here. So as we extend our system by some distance x, what happens is we increase the potential energy in our system by doing some external work on it, and that's going to be where we start thinking about what the total mechanical energy of our system looks like. So at this state here, we have our potential energy that has increased. So our potential energy at, we'll call it state 1, is equal to 1/2 kx squared. And let's call this system at rest here, which means our kinetic energy at state 1 is equal to 0. So we're going to let this thing go, and then it's going to start, as you know, if you let an object on a spring go, the spring is going to pull the mass backwards, and then this thing is going to start oscillating. And then we can start thinking about what the various potential or kinetic energies are as it goes through its oscillation. So as this thing goes back to being completely relaxed, what we have is that our x, our expansion or compression, is equal to 0. Which means our potential energy at, let's call it state 2, is then going to be 1/2 k times 0 squared, which is just 0. And we know that this thing really should be moving now with some velocity v. And so we have our KE2, which is equal to 1/2 mv squared. And so as this thing has some velocity v that's carrying it back towards the wall, you could imagine that it's then going to compress the spring a certain amount until the spring pushes backwards, and we can track what the max compression is going to be. And as it turns out, and you may have guessed, the maximum compression is going to correspond to the maximum expansion that we have put into the system. So what's our third state look like? Our third state looks like this. So we have a spring that's been compressed now with some by some distance x, and it is now stopped and about to, we have a force that is acting on it this way, and so it's about to start oscillating back in the other direction. And so what's that mean? We can now define the potential energy of this third state, and we know that it's going to be 1/2 the spring constant times the expansion squared. And if it's stopped, then we know we can define the kinetic energy here as 1/2 mv squared, but that is 0, so this all just goes to 0. So we know that as we go from expansion through a relaxed state where our object is moving, back to compression where our object has stopped again, we can define our energy at all of these different states. So we can quantify the energetic state of this system as it goes through these different points. And we could actually plot that out. And so we can actually plot out the total energy versus this expansion or compression. So let's mark out our 0 point here, and then let's say if we expand this thing, we can call that the minus x direction, and then we're going to talk about a compression in the positive x direction. You can see, because these all feed into an x squared, just to stay consistent, let's call this minus x, and let's call this guy minus x squared, just so we can plot all these things out. So to sort of break up what we're talking about in terms of potential or kinetic energy, we'll plot both of those on the same plot, but we'll use different colors. So putting potential energy in orange here, let's track what our potential energy looks like. Let's start with the amount of energy at U1, and so when our spring is completely expanded, we have this certain amount of energy, 1/2 kx squared. In state 2, when x equals 0, our potential energy is going to be way down here at energy equals 0 joules, so we have no energy down there. And then at state 3 over here, when we are compressed, we're actually back up to 1/2 kx squared, which is the same as our initial potential energy that we have here. And we can draw a quadratic curve between these things because we know that we have a squared in our potential energy, so it will look like this. So there's our potential energy. We have what should be a symmetric quadratic curve that follows 1/2 kx squared. Now we can track the kinetic energy, and we'll do that in blue. At the point at the energetic state of the system where we are completely expanded and the object is not moving at all, we know that the energy is 0. So that's where we're going to start. When we're expanded, our kinetic energy is 0. There's no energy associated with motion. Once it gets fully compressed, the object stops again, and so we have another kinetic energy equals 0 point here. And then when we are halfway between those, when the spring is completely relaxed, that's when we get our maximum velocity that we have, and that is this state 2 here. And so we know that all of the energy is in motion and our energy associated with motion, and so we have to have our 0 point correspond to U1 up here. And so what's that look like? That looks like 1/2 mv squared, and we have an upside down parabola here. An important idea here is if you were to track the total mechanical energy. Total mechanical energy. Oh, hello. Hey. Okay, so our total mechanical energy stays exactly the same. And so we can note here that when our potential energy is 0, our kinetic energy is maximum, and we have that same total energy no matter what. So similarly, when our kinetic energy is 0, that's when our potential energy is maximum, and all of those things are equal to our total mechanical energy. Now this is an important idea, especially in terms of pulling apart these graphs and thinking about changes in energy at any given state. And really, this applies to what we're about to talk about applies to any conservative set of forces. So just as much as you could think about a spring compressing and expanding, we could also think about a ball being dropped and then bouncing back up, or rolling down a ramp and the total energy associated with a ball rolling down a ramp and then coming back up, and what its energy associated with its height is. All of those things are the sorts of things that you could plot in a similar way to this graph that we've been looking at. So thinking about our potential energy measured in joules versus something like an x distance, and that general plot of potential energy that looks like our parabola here, we can pull apart a couple of different areas on this graph. And so again, you can think of this as, I like to think of it most easily as a ball rolling down this ramp. So here's our little ball, and it can roll down the ramp. And then an important thing to think about is once this ball gets to the bottom here, if it started at some height, then it's going to keep rolling and go back up. But if you place that ball right there and do not do anything with it, then what's going to happen to it? It's not going to move. We can start to think about this idea of equilibrium, or no change in the potential energy. And so that's a really important concept in terms of tracking the total energy of a system, is what the initial energy is and where we have equilibrium points. So if we have some trough at the bottom of the trough, really what we have is a stable point, and so we call that a point of equilibrium. This tracks mathematically, right? If you give zero potential energy to a system, so if you put no work into it and it has no potential energy, then you're not going to have any motion, and that thing will just sit there. And so mathematically, where we find that in terms of, let's say, a potential energy versus x curve, is where our du dx is flat. There's no change in our potential energy, and du dx equals 0. Right? If we put the ball here, then our change in potential energy is going to end up with the ball going downward. But if we just sit the ball somewhere where our potential energy curve is flat, then we end up with an equilibrium point. And so anywhere where you have this condition here, you have an equilibrium point, and that doesn't necessarily have to be the bottom of a trough. Right? We can have u versus x curve. We can have a u versus x curve that is perfectly flat. We can have a u versus x curve that is convex, and we can still end up with some sort of flatness right at this point here. Or we can have our u versus x curve that is concave and have our du dx equals 0 at the bottom of a trough, like we were talking about. Each one of these corresponds to a different type of equilibrium. In terms of a concave situation where you're at the bottom of a trough, we call that a stable equilibrium. So the equilibrium is stable there. If you perturb the system, right, in this case, if you move the ball upward, it will want to roll back downward in either direction. And so we call that a stable equilibrium. It wants to go back to the equilibrium point that it's at. If you have the opposite, if you have a convex system and you're at the very top of, let's call it a hill, and you push a ball in either direction, it's going to want to roll down the hill, and it won't just magically come back to the top of the hill. We call that an unstable equilibrium. Lastly, if you have a completely flat surface and you put the ball on a completely flat surface and push it in one direction, it's not going to necessarily come back to where it was, but it's not going to do something like roll all the way down a hill, and so this guy is neutral. So we have three different types of equilibria: stable, unstable, or neutral. and all of these things sort of track down to what you could think of as a ball on these different kinds of ramps. There's one last thing to say about this, and that's sort of physically or mathematically what exactly du dx is, and we can dig into that a little bit. So we know that u in a certain direction x is going to be the opposite of the work done in x, which is just minus a force in x dx. And so then it stands to reason that if we want to think about what du dx actually is, well, if an integral is just an antiderivative, then the derivative of u with respect to x is then simply going to be the force in the x direction. And so this makes sense in terms of our definition of an equilibrium point here, right? If our du dx equals 0, then that means we have no force in that direction, and so our object is not going to be pushed in one direction or another. So du dx is the change in potential energy with respect to the dimension we're looking at, the distance dimension we're looking at, is a really important parameter. It tells us whether there's a force acting on this thing or not. And if there's no force acting on it, if du dx is equal to 0, then we have an equilibrium point, and we are not going to end up with our object undergoing any sort of motion. So that's the idea of potential energy graphs, and equilibrium points. There's a really important graph that goes along with this in material science, and I'll make a separate video digging into that because it's one that is near and dear to my heart.